Hello everyone, my name is Andrei Marinica. I am a core team developer at MultiversX, and this is the first video in a series through which we want to present you all the technology that we've built, all the tools that we've made available to developers, and ideally to get you started and get you thinking on how to start building on MultiversX, how to use the technology, and how to build cool products. Now, this first clip will be a very, very broad overview of the smart contract framework, on how smart contracts are written and built, and so on. Without further ado, I want to talk to you about, well, several things really, but we're going to start with some really basic tooling, because this is probably the first thing that you will encounter when you start a new project. Now, there are several tools out there. Maybe you've heard of MXPy. MXPy is a bit of a broader tool. It helps you do all kinds of things with our blockchain. But we have actually a much more specific tool designed for smart contract developers, which is called MultiversX SC Meta. Meta comes from meta programming because it also does quite some meta programming. And if you don't already have it installed, of course, you should have Rust installed and Cargo. You just install it like this. And after you've installed it, you can just type SC Meta -H or help. And you can see there all the features that it has, all the stuff it can do. Now, for beginners, probably the most interesting one will be this new one, which will create a contract from a template, so you don't have to set up your project from scratch. So yeah, let's do that. So let's call SCMeta new, and we'll use the other template, which is really, really simple template, and we'll name our new project workshop. And there we go. Right, and now let's see what it has created. There we go. This is the project. It's a Rust crate. It's a workspace. It's a Rust workspace with a crate in it. And now let's have a look at how this crate looks like, what it contains. So let's talk about the contract crate structure, because this is interesting and you will encounter it from the very beginning. So this is our source code file. We only have a single file with code in it because it's a very, very small contract. And immediately you can see we have this Rust crate named workshop, which is annotated with this annotation, which does a lot of magic things that you fortunately do not have to worry about. And of course, some documentation. We always want that in our contracts. Right, and we have a constructor and an endpoint and some storage. We'll get back to them very, very soon. But let's talk a little bit. Actually, before talking about the smart contract structure, let's just build the contract. Why not? So we also use SC Meta to build the contract. It looks like this. The all command, I will talk a little bit about this. It just goes through an entire folder. It finds all smart contracts and does the thing for all of them. In this case, build it. If we had more than one contract here, we would build all of them. This is important because most of the decentralized applications don't only have one contract. The larger apps have actually several contracts, and you want to be able to quickly work with all of them. And the build process, what it produces is this output folder, this one, and you have the WebAssembly binary file. This is arguably the most important product because this is the actual smart contract that will be deployed and run on the blockchain. And if you also want to peek inside, there's a text format for it. It's normally just binary, it's pretty compressed, but there's a textual format to it if you're curious Yeah, so this is the header contract, really, really small. And you also get the contract size, because on MultiversX, we care a lot about smart contract size. We want our smart contracts to be small so they can run fast and consume as little gas as possible. Alongside the binary, the WebAssembly file, we also have an ABI, which is pretty important. The ABI is a description of the smart contract. It tells us what the smart contract looks like, what its endpoints are. So first off, what its constructor looks like, and then what its endpoints look like. That is what their name is, and what inputs and outputs they have, what arguments we should provide to them, and what we can expect to get out of them. It also very conveniently contains the docs you hopefully have written for your smart contract, and some build metadata, like the Rust compiler version, and the smart contract framework version, plus some more stuff that we don't have for this very small contract. So remember, this ABI is important. It not only helps us as humans to understand what contracts are doing, but it also helps tools like the front end or services and stuff like that to interact with these smart contracts. So they're actually also used by other systems. If you want to know more about how these APIs work, and this is a general suggestion that I have regarding everything related to smart contracts, we have a documentation website. And just a second, let me put it on screen. There we go. It's docs.multiversx.com. You find all kinds of information there. This, for instance, is the portal for smart contract developers. And for instance, if you're curious to learn more about the ABIs, you have a page on them. And if you're curious what these inputs mean and how they actually get encoded and decoding, which obviously is very important for any kind of interaction with a smart contract, automated or by hand, then you also have a pretty big specification on the data format, on the codec, serialization, and all this. So I will let you explore this on your own. Right, let's go back to our little project. Right, now let's actually talk about its structure. So MultiversX smart contracts are actually written as pure Rust libraries. So this one is the main library that we have right here, and this is actually pure Rust code. It doesn't know about WebAssembly. It barely knows about blockchain, well, other than it has to define endpoints and stuff like that, but it is not tied to a specific technology. This is a very important point, because we're not only writing code to be used on-chain, to be used as part of smart contracts. The same kind of code will be definitely used in tests, both unit and integration tests. And it's actually very important to write those tests, because this way you can also debug your smart contracts and see if they work correctly. But even more than that, you can use this kind of code also sometimes in an off-chain kind of environment. Maybe you might write a tool in Rust that interacts with the blockchain and that might need some logic that pertains to the blockchain, to the smart contract. So it's very important that these crates are pure. Now, every crate, in order to be built, needs some help. Actually, the ABI is not only a useful output, but it's also a central part of the build process. And every smart contract needs a meta crate. So the meta crate has barely any code. It just references the contract and the framework. But very importantly, this crate is asking the smart contract crate for the ABI, is able to obtain that ABI, and based on that ABI, it is able to perform the rest of the build, to configure the build and make sure that the build is safe, that it complies with the blockchain standard, and so forth. So I did show you the standalone tool just moments ago. So this would be the standalone tool that we've used. But this one, the one that has performed the build, would rather be its smaller sibling, the version of the SE meta crate that is specific to each contract. So we have the same SE meta that is the standalone tool and a build helper and the build coordinator for smart contracts. So that's why don't be scared if you see this meta crate here. It's supposed to be here. It is your friend. And then there's another crate that every smart contract needs in order to build WebAssembly. It's called the WASM crate. Now, this is the only crate that actually knows about WebAssembly. And usually, if you write, if you put these smart contracts in a workspace, in a Rust workspace, you usually will want to exclude this one. Because it's a bit weirder with all its dependencies to WebAssembly and whatnot, and it doesn't usually it doesn't get along well with code coverage and so forth. But you shouldn't worry about it. Its source code is actually always auto-generated, so you shouldn't actually have to write anything in it. You should just forget it exists. And it has some options regarding to how the build should be performed, what optimization levels, stuff like that. You shouldn't worry about it too much. Just know that it exists here and that it is essential to actually building the WebAssembly binaries. Right. So this is in principle the structure of a smart contract. Of course, you're gonna want to have tests here. These will be the integration tests and maybe the scenario tests. But these are not the scope of this video. We will be talking a lot more about this in a future video. Right, so we talked about the contract crate structure. Now let's have a little bit of a look at code in a bit greater depth. We did talk about, we did see a few endpoints, a constructor, but let's see what else is there to be found in smart contracts. Right. So for this, I'm going to abandon for the moment our little workshop project, and I'm actually going to look at just a second. I am going to look at some real contracts from the framework. Is a big repo we have with a lot of these smart contracts, and I'm just gonna go into a few sections of these smart contracts to explore a few of the basic features of what you would find there, and what you would deal with as a developer every day. Now, what we are looking here is the multi-sig contract is a contract that coordinates other contracts and coordinates tokens. It's a way to split responsibility between different actors. So we've already seen a constructor. This is the constructor for the multi-sig smart contract. And you can see some endpoints. Some of them are labeled with view instead of endpoints, and some of them are actually labeled with endpoint. So there it goes. So this is a regular endpoint. This is probably one of the most important things that the multi-sig contract does. It allows actors to sign for things, to approve things. The view endpoints, in principle, should only be read-only. They should just retrieve data. Their purpose is to make it easier to explore the state and the contents of the smart contract. Just a little mention here. Right now, the fact that they are read-only is not enforced. We expect developers to be responsible and not write mutable operations here. It will, though, be enforced in the future at some point. All right. Another thing I want to point out is that smart contracts do not only accept data like arguments and do not only return arguments. They're not just simply computing machines. They also deal with tokens. And in order for them to receive any tokens, they would have to, the developers would have to explicitly specify this. And we do this with the payable annotation. Unless a smart contract is annotated with payable, you cannot actually send money, I mean, eGold or ESD tokens to that endpoint. Otherwise, the transaction will simply fail. It will be rejected. Right? And now that we've talked about endpoints, their inputs, outputs, and the fact that it can be payable, let's look a little bit at state. Smart contracts have state. Otherwise, they would be forgetful and we wouldn't be able to do anything useful with them. Right. So smart contract storage or state is a simple map of key value pairs. There's no constraint and no typing of any sort of the keys or of the values. You can put anything you want inside the keys and the values. But this, for us developers, is not particularly useful. We like working with types. We like knowing where we're looking, what we are looking at. So we have to find some higher level abstractions for this storage. Now, historically, at the very beginning, we used to have these methods, these functions that would directly read or write from the storage. They were like storage get, storage set. They're still available, but they've fallen out of favor. Smart contract developers nowadays prefer to work with the storage using the so-called storage mappers. Now, storage mappers are a way of dealing usually with multiple keys, so with multiple locations in storage. The simplest value mapper, though, is the single value mapper, which is one key, one value. You specify the name of the key. So in this case, it's a symbol. It's a single number. It's called quorum, and the contract will know to look at the key quorum to get this number. But if we want to do like user management, we have users. We have a user mapper which will contain numerous users. Each user will be stored at a different key, so that we can retrieve them a bit easier. And similar in this fashion, we have like lists, like vec mappers are basically ordered lists. We have unordered sets and so forth. There's a wide variety of storage mappers. And they help you not to worry so much about how things get encoded in storage. It helps developers focus on the high-level logic. Right. So yeah, this is storage in a nutshell. Now, I've talked about storage. Yeah, let's talk a little bit about events. So storage is something that is persistent, that remains. It's on-chain, it stays there. But sometimes, just by executing a smart contract function, it might not always be immediately apparent what happened, if we had any error, stuff like that. So what is usually very useful is when writing smart contract code to also from time to time log events. Now these events, they are not accessible on chain. Not even the contract itself has access to them, but they do remain off chain in the transaction logs, and thus it is easy for front end and services, and all the other off-chain systems to query and better understand and index data from the smart contracts. And in order to very easily log these events, we have this annotation called event. Events have a name, and you can either dump data into them, or you can have these like topics or indexed data fields, which in principle are indexed, so they end up in a database where you can easily search for them. For instance, if you are curious to see what kind of asynchronous calls a multisig has sent, who it has called, you can easily index it by, for instance, by the recipient, right? Right, so we talked about, we did talk about endpoints, constructor, storage, event logs. These are the absolute basics of smart contracts. But now let's have our contracts also do something more interesting than that, something more useful. Let's have them themselves interact with other accounts. And the easiest way that they can do that is by transferring tokens, so either eGold or ESDT tokens. And let's see how they would do that. All right. So back here, I'm gonna show you a part of a very important but actually very simple smart contract. Is the eGold ESDT swap. It's the contract that wraps eGold into the wrapped eGold token. So from the get-go, you can see it has two big endpoints, one that wraps eGold and one that unwraps eGold. And they both have to be payable. One of them will have to be payable in eGold and the other one in ESDTs. And of course, we will have to know how much eGold we received. This is how we do this. Call value eGold value, and then we use this amount in our business logic. Now, to send eGold, it's very simple. I just have self, so the contract send, the send component, and direct eGold to whom, how much. To do the same for fungible ESDTs, you do the same, but the method is called differently. It's called direct ESDT, and because they're ESDTs, they also have token ID. In this case, it will be wrapped eGold followed by some numbers, an amount, and the nonce is 0 for fungibles. If they're semi-fungible or non-fungible, this will be non-zero. So this is how you send money basically around very easily. And since we're at this contract, you can do other things too with tokens if you have the rights, of course. You can mint them, you can burn them. Other contracts are able to also issue them or change their metadata, change their attributes, and so forth. So these are the simple ways that smart contracts can interact with tokens and send them around. But now, what if smart contracts want to do a little bit more than that? What if smart contracts want to interact with other smart contracts? Now, this is interesting because smart contracts to call one another, they have to sort of pretend they're around, pretend that they're just like other objects that you can call. Normally, smart contract calls, so smart contract to smart contract calls are not so simple on the blockchain. There's a lot of stuff that is going on behind the scenes. But for the developer, this should not be so important. The developer should only see that these two components, these two smart contracts, just basically call each other as, you know, as you would call a function, you would call a smart contract. Now, if I don't know what contract I'm calling, for instance, back to the multisig. The multisig can work with any contract. It doesn't really know what contracts it's supposed to be calling, so it has to call them in a very, very broad sense. Then it would use some sort of general methods, the same as we did for sending eGold around. For instance, to send an asynchronous call, this is the most general type of call because it can also work cross-shard. You just basically prepare a general contract call like this. And sure, you can add eGold transfer, stuff like that. And you mentioned that it's going to be an asynchronous call. And optionally, you can also have a callback. We are going to talk about callbacks and stuff like that, I think, in a different video. And then call and exit because the old asynchronous calls also terminate execution immediately. Same way you can deploy contracts. This one. So deploy from source contract. You can upgrade contracts and you can transfer execute, which is a different kind of call. So these are all ways in which contracts can call one another without knowing anything one about the other. But this is not so convenient. I mean, in most of the cases, the contracts that will be calling one another know what they are calling. For instance, if you have a DeFi app that is interacting with the X exchange, you will know what you are calling there. And we wanted to offer a type-safe way of contracts to communicate with one another. And to do this, we've invented this thing called proxies. So whenever you want to call a smart contract, it's very convenient to have a proxy, which is like an interface of the smart contract. The blockchain doesn't know about types of these arguments, but we do. For instance, we know that this PayMe proxy receives 64-bit signed integer, and this one receives just a 32-bit signed integer, and this one also received a big number. So these are things that we know as developers, and these are things that also exist in the ABI that we should hopefully have access to. And having these proxies, you can truly then call use the proxies to call the other contract as if you would call just a simple function. So in this case, let's look at this syntax. So we have this proxy, this message me proxy that we're getting. We have to specify where we are sending the call. In this case, we have to give the address. And then we can simply call the proxy this function, which is not the real function in the contract, obviously, because we cannot call it directly. We don't have access to it. But it's an interface that acts pretty much the same way. And it will encode the arguments for you, and it will decode the result if there is a result. So in this way, we have contracts that know each other and are able to communicate in a type-safe way, and not have the smart contract developer worry about encoding or decoding arguments, and basically having better code. So, oh yes, and let's talk about one last thing, and after that, I am going to wrap it up and leave the rest of the content for other videos. So smart contracts can become kind of big. So you don't usually want to have a smart contract in a single file. You might have thousands of lines of code. So which is why the module system is very important. You want to split smart contracts into modules. Now, these modules are simply like mini smart contracts that you can take and integrate into smart contract. This is used to split code, but also to reuse code. And now that I mention this, let me also show you. We have a big crate called modules, which has a number of standard modules that any contract can use. And some of them are really widespread. For instance, the pause module is a pretty common thing to have in a smart contract, the ability to temporarily stop any sort of execution. So it's very easy to integrate just by adding this module and then referencing it in code. Or having stuff like a contract that registers a hero tag, because why not? And so forth. So reusability is also something we're looking at. Now, let's make a short recap, and then I will wrap it up. So we did talk a little bit about tooling. Tooling is basically the SC Meta tool is the one that we mostly use nowadays for developing smart contracts. We did talk a bit about how a smart contract looks like, what the structure of the crate is, what kind of files you would expect in such a project. We did talk a little bit about contract code, about the absolute basic elements of code like endpoints and constructors and storage and event logs. And then ultimately we talked a bit about how smart contracts do things and send the money around, for instance, or call other contracts and so forth. Now, this was just a very basic introduction. stay tuned. The next video will be about testing, which is very important, sometimes even more important than the development itself. So stay tuned for that. And until then, keep building and keep being interesting and doing wonderful things. Thank you very much. See you around.